My name is Irina. I'm the provost of DTU, and I have approved the evaluation committee on the 27th of April 2015, and the academic council has accepted the dissertation for defense on the 22nd of September 2015. And for those of you who don't know, this is really fast track for a dissertation. So we are moving fast in DTU. The doctoral candidate is Irina Petrushina, and the two official opponents are Professor Michael Stoukadis, Aristotle University of Thessaloniki, and Professor Erik Waxman, University of Maryland. The chairman of the assessment committee is Professor MSO Peter Holzapfels, DTU Energi. And at this point, I should ask if there are anybody. We have not received any unofficial opponent requests. That is, that somebody who's not an official opponent can ask to have the word during the defense action or ask a question of the candidate. So therefore, at this point in time, I just have to make sure if there is or are anybody in the auditorium who would like to ask questions of Irina. This is your chance. Don't be shy. It's okay, I will give you a second chance after the official opposition, just so that maybe you hear something that you did not read in the dissertation and which you would like to ask the candidate about. But with that in place, just for your information, as you know, the program is quite straightforward. Irina will give a presentation, maximum half an hour. Then the first opponent will ask questions. Then the second opponent will ask questions. Then I'll actually allow the chairman of the committee also to ask a few questions, since he has indicated and decided to do so. And then I will finally, if time permits, and only if time permits, let unofficial questions ex auditorium come forward. So that is just so that we know what we have ahead of us. As you may also know, we have up to, not exceeding 6 hours. And the door will be locked for 6 hours. No. We will go on for as long as it takes, but of course this is a doctoral defense action. It's something where we do test the candidate to the highest academic level in the fine art of academic dispute. So of course it takes some time to assure that the candidate has the level that we of course expect the candidate has, since the dissertation has been so far approved for this action. You should also know that once the questioning is finished, we will among ourselves discuss whether we feel that the thesis as well as this action has gone so well that we will put forward to the academic council a positive appraisal of the work, and then it is ultimately up to the academic council to decide. So even if we, after this defense action, goes out in right next door here and have a little reception, it is to celebrate that Irina made it this far. But the formal approval has to be given by the academic council. So it will only come later. But I would say it is very rare, as in very, very, very rare, that the academic council would not approve a recommendation from such a learned panel. So with that said, I think we have everything in good order, and I will now let Irina start her maximum 30 minutes of presentation.
Yeah. Good afternoon again, and thanks for coming here to my defense. So, as you heard, my name is Irina Petrushina, and I'll defend my Doctor of Technology degree today, and the title of this dissertation is Electrochemistry as a tool for study, development, and promotion of catalytic reaction. Okay, let's start with outline. So, in the introduction, I introduce non-electrochemists to some basic electrochemistry. And we actually start with discussion the differences between chemical redox reaction and electrochemical redox reaction. And then we go to something in common which put together these two types of reaction. And which gives basis for electrochemical technique to use in study and promotion, and of course in development of catalytic reaction. Then I'll talk about examples which prove this. And the first example will be when electrochemistry was used to study the chemical catalytic reaction on vanadium catalyst, this SO2 oxidation to SO3 on vanadium catalyst. And the so-called contact process. What was new there, that for the first time, we really went deep in this research using electrochemical technique and study not only effect of concentration of catalyst, but also effect and mechanism of cationic promotion and water effect. Next will be a quite interesting piece, which actually has been done almost 10 years ago with my former PhD student Lars Kliman, but now everything is coming back, and it will be about electrochemical promotion of heterogeneous non-electrochemical reactions on a PBI fuel cell system catalyst. And the last one will be really very interesting because we just started this part, and we got something like breakthrough, which could be our Danish niche in development of water electrolysis. So it's very promising electrolyte which can work in the temperature range between 300 and 400. Okay, let's start. My favorite citation from my favorite scientist, Michael Faraday. What he's talking about, I have been so electrically occupied of late that I feel as I hungry for a little chemistry. What a life, no project application. He just got tired and he switched to another area. But it was really useful, this kind of switch, because something crossed his mind that these things hang together under the same law. And of course it was Faraday's law. And that's the feature, the law which put together the chemical and electrochemical reaction. And we'll see how. Okay, so electrochemical reaction, it is heterogeneous redox reaction, which takes, it means that it's reduction oxidation reaction which takes place at the interface between two phases. But we also have chemical redox reaction, heterogeneous. So what is the difference? How can we distinguish chemical and electrochemical reaction? As I tell, so my students probably former know it by heart, these three features. So there are three features which distinguish these two types of reaction. So for electrochemical reaction, it's specifics of interface. That should be the interface between electronic conductor and ionic conductor. Secondly, in electrochemical reaction, reduction and oxidation are physically separated. And as a consequence of this second feature, we have electron crossing this interface as one of the main steps of electrochemical reaction. So, and this specific interface in electrochemistry is called electric double layer. It's actually, according to the last theories, it's, you can call it triple layer. This is, according to this theory, the electric double layer in aqueous solution. Of course, we'll have completely different structure with molten, salt, ionic liquid, solid electrolytes, but it's quite complicated. It can be easily changed by polarization, and then we can change the whole catalytic picture at the interface. Of course, you know these two equations which were discovered experimentally. One of them is one of the main equations in chemistry, which is called Arrhenius equation, another Tafel equation. That's one of the most popular electrochemical equations. So the first one connects rate constant of chemical reaction or rate with the activation energy barrier. So in the Tafel equation, we have connection between current and potential. Both connections are exponential. And it's not something so unexplainable, because it's very easy to connect the current with a reaction rate. It's very simple linear connection using Faraday's law, where N is number of electrons participating in reaction and F is Faraday constant. So what about potential? So if you work with electrochemical techniques and with electrochemistry, you know that the fastest, the best way to change activation energy and the most effect on activation energy will be from polarization, from charging of the electrode in electrochemical system. Therefore, we have very close equations which connected to each other with very simple relations. Okay? Now about electrochemical potential, but not electrochemical potential which we measure and change in electrochemistry, but the thermodynamic electrochemical potential. Of course, most of you know that it's the sum of chemical potential, which is a moving force of chemical reaction, and the electric part, which is the charge of the particles, Faraday's constant, and measured or changed potential during the electrochemical experiment. So this is exactly equal to Fermi level of electrode. If you know the definition of Fermi, I think everybody knows it's the highest energy level occupied by electrons in the metal. This is a basic characteristic of any metal and material. As you can see, it's very simple connection between Fermi level and potential, and how easy we can change Fermi level by polarization of the electrode. Okay, and that's something from my well-known textbook in electrochemistry, Alan Barth. And Fermi level is here. Of course, it is the highest energy level when we have 0 Kelvin. If we are not work at 0 Kelvin, so temperature is different. So we have some deviations. This is 4 kT in both sides. Here, occupied states, unoccupied states. When we pump electrons to the electrode, charge the electrode negatively, it means, so what happens that we increase Fermi level in this way. If it's increased, so then electrons can jump to these unoccupied energy levels and reduce something. If we pump, it's like a water pump, pump electrons from the electrode, charge the electrode positively, Fermi level goes down. And then electrons from this level in solution, this is solution electrolyte, can jump to Fermi level, and these particles will be oxidized. So you can see that it's very important characteristic in electrochemical reaction. What about catalytic reaction? What is the role of Fermi level in catalytic reaction? That's famous Newton's Anderson theory for heterogeneous catalysis. So so most of catalysts are D metals, as you know, and we have this D band which is ends with Fermi level. That's catalyst. What we have at this side, when we so of course reactant here. So we have bonding and antibonding. When we put together two hydrogen atoms, form hydrogen molecule, we have formation of two orbitals, bonding and antibonding. Then this orbital can change, decrease when we have adsorption, chemisorption of a reactant on the catalyst. In this way, if antibonding orbitals reacts with D band, then we could have new bonding, formation of new bonding, antibonding orbitals. And if at least some of these orbitals will be lower than D band, then electron will jump from D band to the antibonding orbital. The result will be what? The result will be that we weaken intramolecular bonding. So that's exactly what we want from the catalyst. So you can see there are Fermi level is one of the most important characteristics of catalyst and electrode in electrochemistry. And electrochemically, we can easily change this. So in this way, we can affect catalyst. We can promote catalyst. So difference between heterogeneous catalytic reaction and electrocatalytic reaction is the number of parameters which affect this reaction. When we are talking about heterogeneous chemical reaction, you know, that's Fermi level, it means that the nature of the catalyst affects. If we are talking about electrocatalytic reaction, we have one more parameter, potential, which can change Fermi level and affect in this way the catalytic reaction. Yeah, so because what I need to change and measure is potential and current, so it's voltammetric measurements. They could be steady state independent on this slow potential scan rate, and it could be cyclic voltammetric dependent on potential scan rates. Here is the best way to study mechanism of a reaction. Here is the best way to define the catalytic activity, the exchange current of the reaction. Exchange current is current in conditions of equilibrium. So it's actually in electrocatalysis, that's the main characteristic of catalytic activity. Okay, so this first example, and people from Helder-Topsoe, they know this catalyst, it's one of yours. So it's vanadium mixed with alkali metal sulfates on silica support. So when you have started this reaction and you produced some SO3, then it reacts with sulfates, producing pyrosulfates. At the temperatures at which this reaction works, so we have formation, as I told you, we have formation of mixture of pyrosulfates, which are molten in this condition. So we have very good simulation here, liquid electrolyte simulation. It's solution of vanadium in a mixture of alkali metal pyrosulfates. This reaction, it's very schematic reaction. During this reaction, catalyst vanadium goes through the cycle vanadium 5, vanadium 4, and backwards. It has been found that by the most of researchers that the rate determinant step is vanadium 4, vanadium 5. So this is one of the most studied reactions, 100 years maybe a little bit less. So, but still there are a lot of discrepancies in these studies about mechanism. It can change from 6-step to 2-step or maybe 8-step. So there were big discussions about how many vanadium atoms active catalyst so contain? Is it monomeric? Is it dimeric? So I'll give you just citations from in form of mechanism and in form of very important thought from two old works. So one is from Gluck and Kinney. They are saying, of course, we can feed all our experimental data in any mechanism which we propose. We just change rate constant. So he told that in order to study the reaction, we should just isolate one step and study this one step independently. What is the best way to isolate than electrochemistry? So in electrochemistry, we can just take out all these guys and left only the main cycle, vanadium 4, vanadium 5. And that's exactly what we are doing. That's actually my design I brought 22 years ago from Ukraine. It's molten salt cell. Here we use, in all molten salt, we use usually silver electrode in a separate compartment. So it was golden counter electrode and it was golden working electrode. Why? Because the last thing we need here is catalyst electrode. We study some homogeneous catalytic reaction. We don't need to study heterogeneous. Gold is not catalytically active. So I have found this, defined the waves, cyclic voltammetric waves, which are responsible for reduction of vanadium and oxidation of vanadium. If you ever use the cyclic voltammetry, it's classic reversible electrochemical reaction when potential, peak potential is not function of potential scan rates. It's only for 2 mol% of vanadium pentoxide. That's the reaction. So what I have found that composition, increase of composition has negative effect on kinetics. So if we want catalyst working well, we need this ideally reversible. So because that will be the rate determinant step, if they are reversible fast, that's it, catalyst is okay. So when we go up to 20 mol%, reaction becomes classically irreversible. So the slowest step is electron transfer. And the best sign of this is linear dependence of peak potential on the logarithm of potential scan rate. So you can just compare this, and you will see the difference. Okay? I calculated, using these equations, I calculated the number of electrons participating in reaction depending on concentration, and that's what it was 1. It was monomeric vanadium. Okay, now we studied the effect of cations. So the well-known promoters in these reactions is sodium, cesium. I introduced lithium. Compare this reaction with this, and you will see the difference. Reaction which was irreversible becomes reversible with small addition of lithium. Look at this. Irreversible, reversible, sodium, small percentage. Look at this. We can actually find the optimum sodium concentration in the catalyst. If you look at sodium content in Topsy catalyst, you will see we were very close. Now, we add cesium again. You can see from, this is the slowest step, you can see the peak potential when we add some cesium independent on potential scan rates. That's the sign of fast reaction. So, looks like, you see how easy it can be done, how easy you can see effect. Just imagine you're doing it with real catalyst and chemically. Then we started a system with sodium and cesium, and we defined on the background. So cesium is in a mixture like 1,1. with potassium, and then we add a little bit sodium. We have found that on these backgrounds, cesium, potassium, optimum concentration will be around here. If you look at industrial catalyst, it will be exactly there. Okay, conclusions. I'll do it fast. So there are so-called big amount promoters and small amount promoters there. So big amount, like cesium, it's 1 to 1 and so on. What is their effect? Their effect is that they change physicochemical properties. So with cesium, we have decrease of melting point, better solubility of products and reactants. That's why cesium usually added in the big amounts. With small ions like lithium and sodium, these are small cations. They have high charge density, so they polarize this vanadium ore bonding and make it easy to destroy it. Okay. For the first time, we actually did try to do study electrochemical promotion using TOPSU catalyst. So commercial like this. I don't know if you still produce them or not. You don't. Okay, so 5 mol% of sodium. So what we did, we use this cell. This was a porous Pyrex. Then we have 2 golden electrodes in the form of mesh. And between this electrode and this porous membrane, we put some, we milled this catalyst, and then we put catalyst particles here. We filled this porous membrane with molten electrolyte, and we got promotion. With negative, not with positive, but with negative polarization. So it was potentials like here, so we pushed this catalyst to work. If you can see with what currents we pushed it, it's currents like, 10 and minus 4. So it's obviously not, it obviously was promotion. It was not electrochemical production. Now it's something which came to us from Patras University in Greece. It's well-known effect called the NEMCA effect, electrochemical promotion, was discovered by Professor Vayanas from Greece. He called it first NEMCA effect, non-Faradaic, and then electrochemical promotion. So what was here? So the basics here is that with the most popular system, if you take not CIO as a catalyst support, but yttrium-stabilized zirconia, which is solid electrolyte, and put platinum electrolyte on it, and put platinum on another side of it, and polarize it slightly, you change Fermi level, and in this way you can promote or slow down the catalytic reaction. And it actually change selectivity. So the main characteristics from Vayanas was rate enhancement, so which just tried to define how different are rates with polarization, without polarization. And his favorite is lambda, where this is open circuit catalytic rate, and this is rate at catalytic current, and this is what's supposed to be if we have pure electrocatalysis. And with this current, which is very small. So it means that if we have the case of promotion, lambda should be very big, very large. These are our publications, and what my input in this theory. So, and I proved it with several examples. Yes, we change by charging of the catalyst. We change the Fermi level. It can be in the form of charge or double layer when we change completely structure of the interface, or we have some small current electrochemical reaction reducing protons or sodium ions, carriers and produce catalytic promoters or oxidized O2 minus. So we actually have catalytic reaction, but this is not reaction which gives us product. It's reaction of production of promoters. And so I gave them these strange abbreviations like EE, P, ED. Here will be just charge of the double layer, and here will be production of promoters. And here will be pure electrocatalysis. So what was chosen is not Nafion system, but PBI system. What was good about this system that actually you can use it at temperatures as high as 200 degrees. So it means that tolerance of the catalyst to CO will be hundreds of times higher. So if temperature of PEM fuel cell is higher than 100, you have better tolerance and you can study more reactions. First reaction under study, we also use mass spectrometer here online, was the reaction when this oxidative coupling of methane, very unusual, very unusual way of this kind of reaction at these temperatures. What we got here is yield maybe not very high, it's around 5, but it's 135 degrees of what acetylene. We specifically use chromatograph to define that this acetylene. And actually, if it's several runs, it could be quite good. This is CO, and here I can show that we have actually we have promotion effect when we have a reduction of protons, negative polarization. So it's pure case of double E, double P. So another one is a reduction of NO with hydrogen. And I just use here slow flow of reactants and high flow. It's about time of contact. If we have slow flow and long time of contact, we just used all active sites. So, and for catalytic reaction will be good if you take these guys from protons from the interface. So, but if it's high rate, then we need some protons come in there and get reduced. That's exactly the case with high flow rate, and that's the case with slow. You can see the NO, how many percent we got with no polarization. You asked me about this case today during today's lectures. Sometimes it's enough to have EMF in your fuel cell system. So it gives right conditions for promotion. Look here, where we have this promotion, we have no current at all. It's a clear case of EDLE. And so I'm very proud because that's Fischer-Tropsch reaction on this catalyst. Platinum ruthenium, because this is CO. Look at the temperature, 170. Look at the yield of methane. If you ever read how high was yield at this 600 degrees SOFC system, it was around 2%, even less. That's because hydrocarbons are more stable at low temperatures. Finally, so, just give me 2 minutes and I'll finish. Okay, that's from our old government. So when they promise that we'll have 30% of energy will be produced through this renewable energy. I mean, maybe with this government it will be 5% less, but I'm sure they will promise 25%. What does it mean? That we need to store this energy, like wind energy. the best way of storage is use water electrolysis at the and then use immediately this hydrogen at car refueling stations. We have, since the last year, we have 3 of them. They produced in some Herning by a little Danish company, which was sold for big money this year. H2 Logic, that's refueling station. That's how they can beat Tesla. Look, less than 3 minutes, 600 kilometers. And it's operation like this. Look, the same. So half of this is water electrolyzer, because fuel cells here are nephron. They need very clean hydrogen. So we produce half of this building is water electrolyzer. What options we have here? We have very old guy, 100 years old, alkaline, cheap. We have very new one. I mean, I'm talking about commercial, very expensive. If we are, almost all companies, as I know now, have their own model of this fuel cell car, hydrogen car. But they are just waiting. If it starts coming up to commercial, real commercial level, we'll need a lot of these stations. We do not have enough iridium dioxide in the world. Even not enough platinum if you take into account that platinum is used in the cars. So we need to get rid of this. So they are quite good with efficiency, but they are very different if we are talking about current densities. 500 here, 2000 here. 2 amps. So it means that it's much smaller than this one. But this is much more expensive. How can we solve this problem? Okay. So first we decided to solve this problem. Okay. 3 more slides. First we decided to solve, just use this usual procedure, like they did with nephron, with PEM electrolyzers. Use PBI. Why not? Just switch the signs and that's it. No, it's not that it, because corrosion get involved here. So it's hot phosphoric acid. We couldn't use even PBI here because it got oxidized at the anode. Corrosion was terrible. The only stable material was tantalum here. Can you imagine this? So, okay. So, but what we did we did 2 nice things. First thing, we diluted a little bit iridium dioxide with silicon carbide support. At least at 90%, it was better than pure iridium. At 3 bar, actually, it was fantastic. That was silicon carbide, and this was on silicon carbide, and this was on pure iridium. Okay, another very important thing, we have shown in phosphoric acid that the tendency of catalyst, tungsten carbide in platinum with temperature range was very different. It was just jump in activity for tungsten carbide, no changes in platinum. So we had suspicion if we can take higher temperatures, maybe we'll prove that this guy will be better than platinum. And these are the temperatures. They are very deserted, no proper electrolytes, just these 2 guys, very expensive, very sensitive to all technologies. So, but we still should know the corrosion resistance. How can we know? Simulation. And thanks to this simulation, we got breakthrough. Because we simulate with this very simple guy, with very low melting point. It looks like this, like water. Vapor pressure is very low. Rolf Berg defined it using Raman spectroscopy. Conductivity, look at conductivity. It's Siemens. It's very high. Moreover, come on. Nickel here is stable. Titanium not active with oxygen. It's oxygen reduction, oxidation, hydrogen reduction. Titanium is stable. Nickel is stable means that much less, so it's closer to neutral acidity. neutral pH, let's say. So, and finally, actually gold is not, come on. It's opposite direction. Come on. So that's what I'm afraid. So just last result and the best one. So with our German colleagues from Technical University of Munich, we proved 100% that in this molten salt, tungsten carbide has much higher activity with hydrogen reduction than platinum. This is after several cycles. So, big hope. Another hope, nickel is stable, so we can use nickel oxide on another side. Very cheap. Okay, that's my conclusions. That's my colleagues from Prague and Munich working with this molten salt and phosphoric acid project. And thanks to DTU for giving me possibility to work in many areas in collaboration with all over the world, with Danish industry. So thanks to DTU Energi, where I finally, and especially Søren Linderud. Without you, Søren, I would never finish this thesis. So, because you really push me hard. And yes, he never stopped asking me, Irina, when will you finish? So, and my favorite group, it's not the last picture, but my favorite, because we still have here our former colleagues. They decided to work for chemistry department. Rolf Berg, where is Rolf Berg? Yes, here, and Jens von Banner. So former Professor Niels Bierum, former head of our group. Professor, where is Professor? Oh, yeah, Olaf Jensen, the present head of our group. Thanks to Professor Lee Quinfeng for PBI fuel cells for my research. And thanks to everybody, guys. And of course, thanks to chemistry department, which I work like 19 years. And thank you for being patient.